Hello, I am not an expert, and today I would like to give you an intuitive explanation to the solution to the Monty Hall problem. So, what is the Monty Hall problem? Well, it's called the Monty Hall problem because it was named after, you guessed it, Monty Hall, who was the first host of the game show Let's Make a Deal, where one of the games on the show was the following. So, you as the contestant are presented with three doors, and Monty Hall asks you to choose one because behind one of them is something great. For instance, maybe a treasure chest full of gold and a couple of sapphires or something. And behind the other two are goats. And you don't even get to keep the goat, it's just symbolic of you losing. Okay? So you don't know which door it's behind. It could be behind this door, or it could be behind this door, or it could be behind this door, right? You have no idea. So you are presented with these three doors. And let's say you pick this one. Okay? So then Monty comes back out and says, all right, looky here. Behind this door is a goat. Do you want to change your answer? Now, the answer of yes or no, that is the Monty Hall problem. And the solution, believe it or not, is you actually double your odds of winning this game if you say, yes, Monty, I would like to switch doors to this other door here on the left. Okay? So that doesn't make any sense, right? It's very counterintuitive. And don't feel bad, because over 1,000 people with PhDs, when this problem's solution first came to light, they all wrote in and said it was hogwash and threw a bunch of fits. And quite frankly, I think it was very embarrassing for the entire PhD community. So let's look at this intuitively, right? Let's say, for instance, this is you, and you are a rational individual, and you've gotten to this point in the game, and you don't know the solution to the Monty Hall problem, and you're thinking about it, right? You don't know whether you should switch doors or not. So you've picked this door here in the middle, right? You have that door. Now, let's say over here, let's say this is like a timeline of your life up to this point. So you were born somewhere over here, and you went to school, and you grow up, and to whatever age you are now. And let's say right about here, you get selected to go to this game show, and here you choose this door. And now, at this point in your life, it could go in two different directions, right? You could have chosen the door that has the gold behind it in this universe, or your life could go in this path. Your life could go down the path of the goat, and you could have a goat behind your door, right? These are the two possible options of your life up to this point. So it's pretty clear that if your strategy is to never switch doors, that you only have a 1 out of 3 chance of winning, right? There's two goats and one chest of gold. You never switch doors, and no matter what happens after you pick that first door, you always keep it. Then you always have a 1 out of 3 chance of winning, right? So let's examine the more interesting strategy of always switching doors. Always switch doors, okay? So let's look at this path of your life, this hypothetical path of your life. Now, we don't know that the gold is behind our door, but let's say that it is, and let's see what happens. So, obviously, if the gold is behind the door that we picked, and we always choose to switch doors when Monty comes out with his two remaining doors and shows you a goat behind one of them, and you say, yes, Monty, I would like to switch doors, obviously this other door also has a goat behind it, right? So if you've picked the gold originally with this door, then you will always lose, right? Okay. So let's take a look at this other universe, okay? This one where we have the goat behind our door. One of the two goats, anyway. So you've picked a goat. You don't know that, okay? Either one of these two things happened. Monty comes out, and he will always show you a door that has a goat behind it, right? So he shows you another goat, but you have one behind your door already. So when you say, yes, Monty, I would like to switch doors, what's going to happen? Right? Well, you're going to get the gold, right? Monty only has one door to choose from if you have a goat behind your door, and he shows you a goat, and you switch to that other door, then of course that one has the gold behind it. So let's recap. If you originally chose the gold, you will always lose, right? Because you switched doors. However, if you started with a goat behind your door, you will always win. When your strategy is to always switch doors, right? Now think about that for a minute. If you start with a goat and he shows you a goat, then yeah, that makes sense, right? If you switch doors, you will always win. Okay. So now let's throw some numbers behind this. I intentionally left them off until this point, all right? So this path we always lost, and this path we always win. Well, originally, you only have a 1 out of 3 chance of picking the gold, right? And this is the always lose path. So you only have a 1 out of 3 chance of losing with the strategy of always switching doors, right? That's the strategy we're looking at. And you have a 2/3 chance of picking a goat. And this path leads to always winning, right? So essentially what's happening is when your strategy is to always switch doors after this new information that there's a goat behind this door, if you always switch doors, you have a 2/3 chance of winning, right? Because this path has a 2/3 chance of happening, and this path has only a 1/3 chance of happening. All right, well, I hope that helped. I know that helped me to think about it, so I wanted to put this out there. If you have any requests for anything else you would like me to do a video on, that would be fun. Hopefully I have time to do it, so have a good one. Thanks for watching. And in my other video, I will do a Java simulation of the Monty Hall problem, because I know that a lot of people, even when they watch this and watch other Monty Hall explanations, they still don't believe that it's true. So let's empirically prove it in my other video, and that'll be in the description below. Thanks for watching.